Hello everyone and welcome to another episode of Interstigation. And in today's episode of Interstigation, we will take a look at four of these shapes: circles, ellipses, parabolas, and hyperbolas. So let's get into it with circles first. So this is the basic circle. Let's draw an axis of it. So that would be a basic axis. This would be the x-axis. This will be the y-axis of things. And let's assume that the center of the circle would be equal to center of the circle would be equal to 0, 0, so that we can do the translation part later, because the translation part would just be for the x term minus h, for the y term minus k. That will be relatively easy, and we will see that in all of the other equations as well, and we've seen that in previous equations as well, like quadratics, sorts of things. So first of all, let's see what we have here. So a definition of a circle is a set of points where the distance from the point to the center, where the distance from the point to center is a set value or a constant. This is called the radius r. So we know our Pythagorean theorem, or the distance formula, that if a point that is x, y, that wants to calculate this distance would be x minus 0 squared plus y minus 0 squared, and all of that square rooted is equal to the distance between 0, 0 and xy. That is equal to our radius r. So we can square both sides to get x squared plus y squared is equal to r squared. And let's see, this side must be a positive number. R is a positive number, so we have no problem squaring it. So let's add the translation factor. For example, let's have a center at here that is hk. Then if we have a circle around this center, then alright, this is not a very good circle. Okay, if we have a circle around this center at hk, we would have that the blue circle over here would have x minus h squared, because if this point is xy, then its x value difference would be x minus h, y value difference would be y minus k, and that our diagonal would be equal to that using Pythagorean theorem. So x plus h squared plus y minus k squared is equal to our r. And that, we know that we can square both sides because r is positive. We have no problem squaring it. So our actual equation of circle would be x minus h squared plus y minus k squared is equal to r squared, where hk is the center of the circle and r is the radius of the circle. And you should be able to go both ways, given a graph and write out the equation, and given the center and the radius or the equation to write the graph backward. So that is all about circle. So let's continue with ellipses. as we did on the previous circles, we should draw out an axis first. So that will be the x-axis, and that will be the y-axis. That is not looking super good, but you get what I mean. So x-axis, and that will be the y-axis. So let's go over the definition of ellipse now. So for an ellipse, there is two foci, or the plural form of focus. So the definition of ellipse is the set of points that has a constant sum of distances from the point to the foci. So basically two focuses, two foci. And that the constant over here that we mentioned, the constant over here will be equal to 2a. And if the center of the ellipse, center will be just the straight dead center of the ellipse, is 0, 0, then the rightmost point will be equal to a0, as it is going x-axis. But if it is having a major axis on the top, then it will have a b0, which we will talk about later, and a constant sum of the distances from the point to the foci. So let's see why that is 2a. So just for this point, this distance plus this distance must be the constant, right? But we know that the ellipse is perfectly symmetrical, so this distance right over here would be equivalent to this distances right over here, and this coordinate over here will be negative a0. Therefore, the whole distance after the transformation, which is a constant of the sum of the distances, would just be 2a. So let's continue our thoughts. Next, let's define this minor axis that we have in our ellipse. Minor axis is the shorter side of the ellipse, which is basically closest to the center of the ellipse. And the major axis, which is a0 and negative a0, if the center is at the center is at 0, 0, is the farthest point from the center of the ellipse. And this point, if the circle is like this, having a major axis on the x-axis, then this point would have a coordinate of 0, b, and this point would have a coordinate of 0, negative b. Now, we know that the sum of the distances would be a constant, which is 2a. Let's draw this triangle right over here. And this triangle would be a isosceles triangle, which it doesn't look like it because my diagram is not very good, but this is an isosceles triangle because it's symmetrical. And because that 2 points are the sum of the distances will be 2a, each of the distance will be a, and this distance would be b. Therefore, the distance from foci to center would be equal to c squared is equal to a squared minus b squared. Notice this is not the Pythagorean theorem, so the representation of ABC might be different. And don't confuse it with c squared is equal to a squared plus b squared, because that is the Pythagorean theorem, and it does have things to do with Pythagorean theorem, but each side is named differently. So this will be c. So now let's derive the equation for our ellipse. Let's say that a point on the ellipse has the coordinate x and y, and it has the two distances from the two foci. This is the two distances that we have. So the first distance, xy to -3, -c, 0 would be equal to square root of x plus c squared, that is plus y minus 0 squared, and that plus square root of x minus c squared plus y minus 0 squared is equal to 2a. Let's move this expression to the other side of the equation to help us reduce the roots, the radical sign that we have over here. X plus c squared plus essentially y squared, because y minus 0 is just y, and 2a minus this whole sort of kind of messy thing. And let's square both terms to get that 4a squared minus minus 4a times this thing, which is still over here. Don't forget to add this thing, and plus, remember this sign is plus, x minus c squared plus y squared. And this side would just have everything except that there's no radical anymore. And we can simplify this to be x squared plus 2xc plus c squared plus y squared, and this will be 4a squared minus 4a times x minus c squared plus y squared plus x squared minus 2xc plus c squared plus y squared. And we notice that there are some terms that we can cancel out over here. So these are the terms, and we can rearrange them again. So let's move the radical to one side of the equation so that we can factor it out eventually. And this side will have 4a squared minus 2xc plus 2xc minus 2xc. So that would be equal to minus 4xc over here. And we notice that there is a common factor of 4. So let's factor that out. That is not a problem. And let's square both sides once again to get rid of this radical. So we have that a squared times this thing. I'll just use brackets over here to differentiate these. Y squared is equal to a fourth times this 2a squared xc plus x squared c squared, and a squared times x squared minus 2xc plus c squared plus y squared. Actually, we can use parentheses instead of brackets because there's no parentheses inside of the brackets anymore. And that would be what we have over here. And let's factor the whole thing out. A squared x squared minus 2a squared xc plus a squared c squared plus a squared y squared. And that will be equal to a fourth minus 2a squared xc plus x squared c squared. And this, what we have here, also has a common term that we can cancel out over here. And we can move one of the sides for it to have the x, y terms, because we know that it will be sort of similar to the equation of a circle, because it is essentially the same thing, and the conic sections, they have a connection between each other. So let's move x and y to one side. So a squared x squared is still on this side, and we have x squared c squared. So x squared c squared. Notice that's minus over here, and that's plus a squared y squared is equal to a fourth minus a squared c squared. Notice that some of these can be factored, so let's try that. X squared times a squared minus c squared plus a squared y squared. And that, does this expression look familiar? It is essentially the same thing as this expression over here, and we can manipulate it to be b squared is equal to a squared minus c squared. So all of these are just basically b squareds. So x squared b squared plus a squared y squared is equal to a squared b squared. And that, let's put this fraction in front, that can be one of the terms, but one of the forms of an ellipse equation. But notice that b is actually on the y side if this is a horizontal ellipse, so to say. So we prefer it to have corresponding terms so that we don't get confused. So let's divide both sides by h squared b squared. We would get 1 on the right side of the equation, obviously, and we will get x squared over a squared plus y squared over b squared is equal to 1. And that is a standard, or so to say, normal equation, or the base equation of an ellipse equation, or a parent equation. And that in this graph, let's add in some more stuff. So an ellipse can be vertical, such as this ellipse, and that the AB term has to be switched because A obviously here is the greatest number over here. So what we want, if it is a vertical ellipse, we want it to be x squared over b squared plus y squared over a squared is equal to 1, so that the a squared is the largest number. And now let's add in the translations. The translations are pretty similar to circles, where it has a minus h, minus k, basically pretty similar to every function that we've learned. Quadratics, cubics, even cubics, square root functions, all of the functions that we know. So what we have would be turned into x minus h squared over a squared plus y minus k squared over b squared is equal to 1. And that is our standard equation for an ellipse. Alright, there's one more thing about ellipses that we need to take care about. That is eccentricity. So, eccentricity. And eccentricity can be expressed using the Greek letter E, which obviously don't pronounce as E, but that represents that. And eccentricity is equal to c over a. And by definition, eccentricity is always positive between 0 and 1. We don't need to remember this. So we know that this length is equal to c, this length is equal to a, and this is the right angle. What do we know? What do we know about c over a? That is essentially the cosine value of this angle. This theta is equal to cosine theta. And that, since cosine theta is from here all the way to possibly here, we know that the cosine theta value is, or theta value is definitely from 0 degrees to 90 degrees. Therefore, the cosine theta value definitely ranges theta. Then cosine theta value definitely ranges from 0 to 1. Now notice 0 degrees can be achieved actually, and that is a circle. A circle is a special type of an ellipse, just like a square is a special type of a rectangle. And that is our domain of eccentricity. And when you think about eccentricity, it is just the cosine value of the theta, and you don't need to memorize the domain or anything about it. And that is about it for the ellipse. Now let's take a look at parabola. Parabola is actually very easy to identify in the general form of the conic section, and we will talk about the general forms later. And because it only has one x squared term as opposed to both x squared and y squared term, a parabola can also have a y squared term but not an x squared term too. So let's continue by drawing the axis first. I know this is not super good. I can just select it and move the vertex to our origin. Now that is our x-axis and that is our y-axis. We know about parabolas before. That is just quadratic, right? Parabolas are just quadratic, such as y is equal to x squared, or more specifically, y is equal to a times x minus h squared plus k. But we need to forget about it in the conic section unit, because that is a very, very different definition of a parabola that we are talking about. So let's forget about all the things that we know, and let's proceed with a new definition of parabola. A new definition of parabola, we know that both circles and ellipses have something to do with distance, so parabolas too. The first parabola has a point inside the parabola, inside the bowl kind of thing, that is called the focus. I'll just say F, so F, focus. And there is a line below, or on the other side of the focus, it's called directrix. Directrix. And that it is a set of points, with the same distance to the focus and the directrix. So let's take a look. Let's say this point on the parabola, this distance and this distance are equal and they're forming a line. So let's call this distance a P, because we will use that later. And if we have this point, then this distance over here and this distance over here, although it doesn't look like it, but it is actually equal distance. It's just my graph that is not the best. And this is the right angle because of the distance. And these all sets of points with the same distance to the focus and the directrix is called a parabola. Now, there's a new term called the lattice rectum. So a lattice rectum is a line segment parallel to directrix that passes through the focus, and its endpoints are at the parabola. This is called a lattice rectum. And these are called the endpoints of the lattice rectum. And we know that its distance, its length, would be 4p, and we'll talk about that later, and we'll prove that in fact. So now let's think about this. If we have a parabola that its vertex is hk, then what is its focus point, its coordinate? So let's consider if it is going up or down. Then, because it is inside it and it's going up, then it has a distance of p away from vertex, so it would have hk plus p. And for directrix, also up and down, I will just copy that over. Actually, for directrix, also up and down, would have y is equal to k minus p, because it is actually below the focus, below the vertex. Now, you may notice that it can open down too. What that means is that if it is opening down, then p is less than 0, or a negative number. So let's see how p is less than 0. If p is less than 0, then let's just change to a different color. Then the p would be, the focus would be below the actual vertex, let's say over here. And if it is, then the directrix would be above the actual vertex, which is actually about over here, let's say. And now let's draw a parabola using these, and instead of going with the same distance and the focus and the directrix. So that will be around like this, with it will be like about like this. So that also tells us that the focus is always kind of inside the actual parabola. Now, let's get started by actually stating the equation of the parabola. We know that the parabola is something to the square plus something, which is a quadratic. So let's see. We know that the distance from the focus to the point and the distance from the point to the directrix is the same. If we call this point xy, then the distance from this point to the focus would be square root of x minus, because the focus would be at h, so x minus h squared, plus y minus k minus p squared. That is our distance from the point to the focus, and the distance from the point to the directrix would just simply be y minus the k minus p, so which is equal to y minus k minus p. And actually we need an absolute value sign over here, just because this value must be positive, right? But this value, if p is negative, might be negative, so we need an absolute value sign. But next step, it doesn't matter because we're squaring both sides, getting x minus h squared plus y minus k minus p squared is equal to y minus k plus p squared. We can move this expression to the right to get y minus k plus p squared is equal to, minus x minus k minus p squared is equal to x minus h squared. Therefore, x minus h squared, using the difference of square formula, we can get y minus k plus p plus y minus k minus p times y minus k plus p minus y plus k plus p. So what we have here would be this. So let's get a blue. So this cancels with this, and this gets 2y minus 2k times that this cancels, and this cancels to get 2p. So, and this left side will still be x minus h squared. So the final equation that we have over here will be x minus h squared is equal to 4p times y minus k. That is our equation for the parabola. And of course, the parabola can open right and open left as well. Therefore, because they're just going to be inverse functions if it is opening right or left, or because they're going to be inverse functions, we can just switch the role of x and y. But y always follows with k and x always follows with h. So another form would be y minus k squared is equal to 4p times actually x minus h. And that are our equation for the parabola. And let's get back to the lectus rectum. If we put this y value back in, let's find the x value that we're looking for. So we're using this equation over here. So let's plug that y value in. Y value is equal to k plus p. So x minus h squared is equal to 4p k plus p k. 4k k plus p minus k. So 4p squared is equal to x minus h squared, and that would give us 2p is equal to x minus h. Actually, that has to be the absolute value of 2p, and x would be equal to absolute value of 2p plus h. And for the other one, it would be the same thing. So p would either be positive or negative in this case. So what we actually have over here is positive or negative, right? So if we get rid of that, we actually get positive or negative. So easy to see that x1, the first opportunity would be 2p plus h, and the second point would be positive 2p plus h, and their distance, of course, would be 2p plus h minus negative 2p plus h would be equal to 4p. Therefore, our length of the lactus rectum would be 4p. And that is about it for parabola. So now we're on our last conic sections, and that is our hyperbola. This is also the toughest and the hardest to deal with in our foreign conic sections. Let's review them: circles, ellipses, parabolas, and hyperbolas. So let's see. Let's draw a hyperbola first. You can see that we're starting from a blank view as opposed to the basic shape that I have prepared for the first few conic sections. That's because the drawing for hyperbola is a bit different, and we're going to start off by drawing the axes. So here is our axis. Should have a little bit thicker pen, and just write that. If we have an a value over here, we need a value, so negative a, and on the opposite side, the same distance have a, and that does not seem like the same distance. Alright, so the same distance a, and we have b, so that will be negative b. And if we draw a kind of a box-like thing, a rectangle around a and b, then we have two asymptotes over here for hyperbola. It's not very straight. I apologize for that because I don't have a dashed line tool. So here is our asymptotes. Now we need a new thing to work with over here. Now let's think of the horizontal ones first, because horizontal ones are more, basic ones. And if we have horizontal ones here, this is the vertex, these are the vertices, then we would have a hyperbola that is infinitely approaching the asymptote. That is the definition of asymptote, infinitely approaching it. However, it does not cross it at any point or even touch it. So here we go. That is the right side of the graph. Approximately, it is like that. And we know that hyperbola is something like this. Oh, we want it to be rounded. Oops. Goodness doesn't like me. Okay. So we want something rounded over here. I'll just write it with my pen. So just like this. And that the slope is definitely approaching infinity at the end. But hyperbola, that is different. In a hyperbola, the slope is actually not infinity, and it goes like this. The end, you will see like it approaches kind of like a straight line, but it's not. And here we draw the other quarter of the hyperbola. Notice that there are two pieces for the hyperbola, and these are all the components that you need to draw an hyperbola. I did not draw it very symmetrically. As you can see, this side is very different from the other side. And that is our hyperbola. Now let's go over the definition of a hyperbola. So there are two foci in hyperbola, too. That is inside the curve. Inside the curve, similar to parabola, that is inside the curve, two foci. Their distance will be called c. And we have the difference. So a set of points which has a constant difference constant difference of the distances to the foci. Basically, the distance from like this distance minus this distance, the absolute value of that would be a constant. And that constant is also 2a. Because, as we can see over here, if we take this point connected to over here, that would give us this length, and this point to all the way to the other foci will give us that whole length. And notice that it's not this length over here. It is not that whole length. It should be from here to here, because this is the actual point that we're picking. And this length minus this length these two would cancel out because they're symmetric, and our distance would just be this portion, would just be 2a. Now, let's try to derive our formula for hyperbolas. Let's just try C right now. I'll tell you a relationship that works, and we will try to prove that backwards after we derive the equation of the hyperbola. So C, as in relation to A and B, as you might have guessed it is that C squared is equal to A squared plus B squared. And that it's very similar to the c squared is equal to a squared minus b squared in ellipses. Alright, let's not get distracted by ellipses and let's continue on with our thing. Now, if we have a point xy, then its distance to one focus, this point would be, let's say that the center over here would be hk, then this coordinate would be h plus c k, right? Or it could be hk plus c, because it can be vertical as well. Remember that. And vertical is basically the kind of inverse function. And let's say that this focus would be h minus c k, and the distance from this to this, let's call this d1, and distance from this to that, so let's try to write that, this whole distance over here, let's call that d2. So what we have is d2 minus d1. Remember the absolute value because it has two pieces to each hyperbola. d2 minus d1 is equal to 2a. d2 is equal to square root of, let's give us some space over here, square root of, let's say that x, h minus c, so x minus h plus c squared plus y minus k squared, and plus or minus actually that d1, which would be x minus h minus c squared plus y minus k squared, which is equal to 2a. And don't forget our absolute value over here. So if we move one of these to the other side, now absolute value cannot be broken down over here, and two distances might be that, but notice that we will be squaring both sides soon, so the absolute value does not matter as we are squaring both sides. So it would be equivalent to, as this is not very rigorous over here, but it will be equal to that 2a plus x minus h minus c squared plus y minus k squared. That squared, let's keep that, it will be equal to that, as since we're not squaring both sides for now, but it will. So but technically what we gotta do over here is to have two cases over here. One case will be this difference would be 2a, one case this difference would be negative 2a, but since we're squaring both sides, that would eventually combine to one equation again. And I know this is not directly equal to this, so not very rigorous over here, but that works. I'll just tell you that. And if we square both sides, we get 4a squared plus 4a square root of x minus h minus c squared plus y minus k squared, that plus x minus h minus c squared plus y minus k squared, and that would be x minus h plus c squared plus y minus k squared. And we can cancel this term out. We would get that x minus h plus c squared minus x minus h minus c squared, that minus 4a squared is equal to 4a times all of this nonsense. And that we can use the difference of square on this portion of the equation to get that x minus h plus c plus x minus h minus c times x minus h plus c minus x plus h plus c minus 4a squared is equal to 4a. This process is similar to our parabola, but we have one more square root to go. So over here what we have is that would be c canceling out, so 2x minus 2h, and this would have x and h cancel out, so 2c. What we have at the end over here would be 4c times that x minus h over here minus 4a squared is equal to that 4a times x minus h minus c squared plus y minus k squared. And now we can cancel out our 4 on both sides of the equation to get this. Now this, let's move this and square both sides. We get this, minus h minus c squared plus that a squared times y minus k squared. And this side, squaring both sides, what we would get is this term squared, and add this term squared, or this term squared would be a fourth, and minus 2 times a squared cx minus h. Kind of confusing at first, but I promise we're about done. Now, let's see what we have for x term over here. So we would have those, and let's see what we have for our x term first. So x term, we have this over here. So c squared times x minus h squared minus 2a squared c x minus h minus 8a squared minus times that squared, and that is our x squared term. And now this, how can we simplify this? Let's see. We have the kind of annoying minus c over here, and we would try to get rid of it, as x minus h looks pretty sweet over here. So let's try to use another variable. I will use another color. M is equal to x minus h. And now be c squared m squared minus 2a squared cm minus a squared m minus c squared. And now let's see how far we can simplify it before we plug it in back to our original equation. So over here we have c squared m squared minus 2a squared cm minus a squared. Let's expand that out. M squared minus 2mc plus c squared. That would give us c squared m squared minus 2a squared cm minus a squared m squared minus 2mc plus c squared. So minus 2mc, so plus 2a squared mc minus a squared c squared. And that we can conclude that this and this are the same, so we can cancel them out and get c squared minus a squared. Let's get the m squared out, minus a squared c squared. And let's plug that back into our equation, and that is actually the expression of these three crossed off expressions. So what we have over here would be c squared minus a squared m squared minus a squared c squared plus 8/4 is equal to a squared y minus k squared. Now First of all, let's move the y terms over and the ac terms to the other side, and we can plug m back into our equation. So what we have here would be c squared minus a squared. That will be x minus h, as we set over here, squared. That will be minus 8 squared y minus k squared. That is equal to a squared c squared minus 8/4. And we know that c squared a squared, according to our relationship up there, we can get that c squared minus a squared is actually b squared. So c squared minus a squared. So this, if we factor it out, we would get that a squared times c squared minus a squared, that is actually b squared. And that is b squared 2 times that minus that. And let's divide both sides by a squared b squared. We would get, at the end, we would get that is equal to 1 x minus h squared over a squared minus y minus k squared over b squared is equal to 1. And now, as I've said, it can be vertical as well, such as like this. Well, that equation would just simply be kind of the reverse of this equation, which is y minus k, as we know y always follows with k, squared over a squared minus x minus h squared over b squared is equal to 1. And notice that a squared is always on the positive term over here, and that x minus h or y minus k, that if the positive term is x term, then it's left and right with the axis cross parallel to the x-axis. And if it is y minus k that is positive, then of course the axis is parallel to the y-axis. And now let's get back to our this equation, and we said we're going to prove it. So let's actually draw a cleaner image so that we can prove it over here. So if we have this, let me get a thinner pen. So if we have this and a parabola, well, this thing doesn't want me to draw a parabola today. I'll just hand draw it. It is not going to be the best, Okay, my hand shook. So if we have that, and if we copy this to the other side, that would be great. So I guess I can't copy it. I have to copy over here. So copy, paste. Let's reverse that and get this. So okay. Now this is a parabola. Not so well drawn, but that's a parabola. Let me actually see. I can't move it anymore. Okay. Let's see. Let's draw that over here. Alright. That's a parabola. Let's draw kind of a box thing over here. We don't need more. We just need the b information over here. So from the focus, the two foci, let's draw a vertical line to the x-axis. That's assuming that the hyperbola is horizontal and the hyperbola is actually centered at 0, 0. So now let's have this line over there. So that is our right triangle that we can use Pythagorean theorem on. And over here, this coordinate would be x coordinate would be c, because this distance would obviously be c, and that would be y. So this distance will be y. Let's set that to y. And that by definition of a conic section of a hyperbola, this distance, this whole distance, would be equal to y plus the 2a. And this distance would be equal to 2c. And we have over here 2c. So by Pythagorean theorem, what we have over here would be 2c squared plus y squared is equal to our y plus 2a squared. Let's try to simplify this a little bit. 4c squared plus y squared is equal to y squared plus 4ay plus, that is 4a squared. And let's cross that off. That would get us to that 4a squared plus, let's just cancel out that 4 over here. A squared plus ay minus c squared is equal to 0. Let's just write that as is equal to c squared, because that is not our final form either way. So let's do that. And let's plug that into our equation that we just derived. So, a squared plus ay is equal to c squared. What we have over here is that this thing is a hyperbola, and hyperbola goes with this equation, right? Now, what we have over here would be, let's plug this point in, cy. So c would be the x, c squared over that x squared, or c squared over that a squared. Let's show that. C squared over that a squared minus that y minus k. So y squared minus b squared is equal to 1. Now we solve that. We need to solve for y over here. We can get y is equal to c squared minus a squared over a, which if we plug that y in, we can get that c squared over a squared minus that, plug that y in, so c squared minus a squared squared over a squared b squared is equal to 1. And now let's put these, so multiply both sides by a squared b squared, I guess. That is equal to b squared c squared. What we have over here, we can move this to that side and this over to this side. We get that c squared minus a squared squared would be equal to b squared times c squared minus a squared, and that can cancel out one of them. So we get that b squared is equal to c squared minus a squared. And that also gives us that c squared is equal to a squared plus b squared, which is exactly what we have over here. Now, one last thing about hyperbolas. One last important thing, because hyperbolas are like parabolas, like double the parabolas. Although the shape is slightly different, there is lacteus rectum, there is directrix, but we're not going to talk about those. And they're like ellipses. There is eccentricity in parabola, and it is still c over a, but we're not going to talk about that either. Well, we are going to talk a little bit about that. Eccentricity is equal to c over a, which is larger than 1, according to this formula. So that is very different from the range of eccentricity for ellipses. Now, one last thing that we're going to talk about is the equations for asymptotes. First of all, let's find the slope for the asymptote first. Let's just count boxes rise over wrong, or changing y over changing x. So changing y over here, let's get a different color over here. Changing y over here would be b, right? Changing x over here would just be a. So the slope would be b over a. Or there's another asymptote this way, so that's negative b over a. So what we have over here would be, let's use point slope, point intercept form. That would be not point intercept form, point slope form that always goes through the center of the hyperbola, which gives us y minus k is equal to m, which is b over a times x minus h. And that we need to be careful to add plus or minus sign over here because there are two asymptotes over here. And for the vertical ones, because the a and b are on different x and y's, we need to make sure that it is kind of actually flipped. So it will be, so horizontal, vertical would be y minus k is equal to plus or minus a over b times x minus h. Which is confusing. You might not be able to remember it, but remember the definition of a slope point slope form, which on test you can just count boxes, and for that slope it is pretty easy and pretty obvious over here. Thank you for watching this episode of Interstigation, and have a great day. Also, please put your question down in the comment section below.